Okay, hello physicists, circular motion in 3 minutes. Now I'm actually going to start a timer to make sure that I don't go over the 3 minutes. So it's a nice wee video for you guys. So circular motion in 3 minutes. What's important? Circular motion obviously is anything moving in a circle. So I'm going to have things that are moving in a circle. So I'm thinking that anything moving in a circle is going to have a centripetal force on it, pulling it towards the center of that circle. Just put this on silent actually. So I have a centripetal force pulling me towards the center of the circle. We know anything that has a centripetal force is going to have an acceleration. So that's why anything going in circular motion has an acceleration. Again, we can see that because right here, it would move in this direction. That would be my linear velocity. Whereas right here, it would move in that direction. That's my linear velocity. So we can see the velocity is changing over time, and that's why it's accelerating. Because acceleration is a change in velocity over time. So again, we know it's accelerating because remember, velocity is a vector, and because its direction is constantly changing, that's why it is accelerating. When things undergo circular motion, we can write acceleration differently. Acceleration we can write as v squared over r. So that's our linear speed squared over r. Or we can write it as w squared times by r. A lot of people don't like me writing w. Yes, it is lowercase omega, but let's just save yourself some time. It is a w. So w squared times r. W is our angular speed, okay? Rule of thumb is anytime it mentions speed in your questions, it's always talking about linear speed unless you see the word specifically said angular speed. Remember what an angular speed is the angle goes through in a certain time. If it does a full circle, that angle is 360 degrees or 2 pi radians. And if it does a full circle, that time becomes capital T. So you can see that angular speed is 2 pi over its period. Or the angular speed can be written as 2 pi times by the frequency, okay? And its unit is radians per second, okay? That does not mean your calculator has to be in radians. Your calculator can stay in normal mode because you're not using sine or cosine anywhere here. So it can stay in normal mode even though the unit is radians per second. Again, does not mean you have to put into radian mode. Okay, questions that could get asked about this. One question could get asked about this if we have the Earth and I have a satellite that is orbiting the Earth. And I want to figure out what is its linear speed. So I want to figure out what is its speed of orbit, okay? We know that that centripetal force pulling it towards the center of the circle is due to gravity. So we know that force is due to our gravitational field, which is G, m1, m2, divided by the distance between them squared, is going to equal the mass times by v squared over r. So again, this is our force because of the gravitational attraction between them. First, it's in gravitational fields. And it's my mass times my acceleration. I'm using this equation because I want linear speed. Now, the key thing people forget is it's the satellite that's doing the circular motion. It's the satellite that is doing the circular motion. Okay, we'll stop here then. There's a satellite that's doing my circular motion. So the mass here is the mass of the satellite. So when you cancel out the masses, it's the mass of the satellite you're canceling out, the thing that's doing the circular motion. And the mass that remains is the mass of the Earth. So what I can see now is I can multiply both sides by r squared and get that gm is equal to v squared, r squared over r times by r. So now I can find that v, that linear speed, is going to equal to the square root of gm over r. G is our universal gravitational constant, shown on your formula sheet. M, again, is going to be the mass of the Earth, the larger thing. And then r is your radius of orbit. Key thing is you have to include the radius of the Earth here. It's from the middle of the Earth all the way to the satellite. So make sure you include the radius of the Earth and the height of the satellite in your equation.